and welcome back to Geography 110. Over the last 2.5 weeks, we've been taking a look at the exciting world of biogeography, but now it's time to move on. Some of the concepts and topics that we learned in biogeography, most especially dealing with political ecology, for example, are going to continue to reemerge throughout the semester. Other aspects, such as biomes and pyrogeography, you may not see those topics again for another couple of weeks or probably at the end of the semester on our final exam. So, what do we have coming up? Well, over the next week and a half, 2 weeks, we're going to be taking a look at Earth tectonics as well as Earth materials and getting a good understanding for geology, for example. So, in this first lesson, we're going to be taking a look at magnetism, the makeup of the Earth's core, mantle, and crust, beginning to just get a brief understanding for how plate tectonics work. Then we're going to be progressing into how you extract oil and gas. Then, after that, learn about the various sorts of rocks that are around us. And then we're going to wrap up this unit by examining earthquakes and volcanoes here towards the end of the next week and a half, 2 weeks from now. So as you can see, we have a variety of really exciting topics ahead, and let's go ahead and get started. So as I mentioned in the introduction, today we're going to be looking at really just sort of the beginnings of geology and give you a basic vocabulary that we're going to be using for the next week and a half, 2 weeks, and then later on, again at the end of the semester when we examine geomorphology. I know the title says Earth Materials and Tectonics. Today is going to be much more focused on Earth materials. Tectonics will emerge again when we start talking about earthquakes and volcanoes, and to a lesser extent, just rocks in general, and that will occur sometime next week. So what are we going to be taking a look at today? Well, specifically, we're going to be taking a look at the time scales of Earth and learn to get some vocabulary under our belt, dealing with eon, super eon, era, period. For some of you who have taken a basic geology course in the past, this is going to be a complete review. For those of you who have never taken a geology course, this may be a little bit of a peculiar subject, but we'll walk our way through it. The next thing is going to be talking about basic geology, learning about the layers of the Earth's subsurface, starting at the core and going all the way out to the crust. And then we're going to end today's lecture by examining a little bit of magnetism and how the Earth creates its own sort of magnetic sphere. So first things first, what is geology? Because this is going to be our key focus for the next week and a half, 2 weeks. Geology is the science that's concerned with the solid Earth and looks at the rocks and processes and how they change over time. Geologists are, for the most part, focused on abiotic factors, learning about how gravity affects rocks or how planets affects rocks, right? But more recently, there has been interest in biotic factors, as I'm going to show you in just a second. Geology has a bunch of subdisciplines, just like geography, and some of those subdisciplines overlap with geography. So you don't need to know all of the subdisciplines for the test. This is just purely for showing you the various sorts of geologies that exist out there. So we have everything from biogeology, which studies how the biosphere and the lithosphere interact with one another, environmental geology, geophysics, mineralogy, petrology, sedimentology, stratigraphy, which we're going to be talking about here in a minute, volcanology, which we're going to be examining here in the last lecture of this big unit. And so there's a lot of different perspectives from which you can examine geology. I also would like to say, too, that there are some fantastic geologists at UNC. And so if you like this particular unit and would like to learn more about geology, I'd highly encourage you to take an Intro to Geology course here at UNC. So what are the things that we're going to be focusing on today in this unit? we're going to be focusing on endogenic systems, which are basically geologic systems that originate within the surface of the Earth, processes that are driven by the heat of the core of the Earth. And so here in a little while, we're going to be talking about the Earth's magnetism. We're going to be talking about plate tectonics and earthquakes and volcanoes. All of these things happen because the Earth is the Earth, not because of its relationship to the sun or its relationship to other celestial bodies. Exogenic systems, on the other hand, which is basically processes that happen on or above the Earth's surface that changes the Earth's surface and that may incorporate some energy that may not come from the Earth's core or the Earth's mantle. And so when we think of exogenic systems, we may think of tides or wind or rivers, or even, for example, biogeography. But exogenic in the context of geology is really looking at how Earth's surface landforms change over time. We refer to this as geomorphology. And this is something that geographers really take a look at. This is where there is immense overlap between geographers and geologists. I myself have done quite a bit of coastal geomorphology research in my background, so seeing how coastlines change over the course of time. This is a topic that we'll be delving into, all the various sorts of geomorphologies, right in the last 2 weeks or so of the semester. So the main thing that geologists, the main sort of foundational topic that geologists focus on is geologic time. And there's a couple different ways that they approach geologic time, as was discussed in your book. The first of which is the numerical age of a rock. And that's always done relative to the present. So you might say a rock is 500 million years old relative to the present. This type of dating of rocks is done through radiometric dating, which is very similar to the type of work that our guest lecturer, Carly Schmidt-Simard, talked about earlier in the semester, as well as what Professor Hernandez talked about during his global warming lecture right before your first test. So that's one way to approach aging. Another way to approach aging is through a relative age, which is examining the age of a rock as compared to other rocks. So we, as some of you probably already know, rocks just layer on top of one another. And so you'll be able to tell the age of this layer of rocks versus, for example, that layer of rocks. Examining differences across layers of rocks is a process that's referred to as stratigraphy. So in this photo that I took from the Grand Canyon, we sort of basically know that from here all the way up until we reach that first white line, those rocks were laid down 280 to 340 million years ago. Then there's a little bit of a break, and then you have these different sorts of rocks that were laid down between 270 and 280 million years ago. Then there's another break. You can tell that the rocks change both color and sort of texture. And then at the very top, we know that those rocks were laid down between 270 million, or laid down about 270 million years ago. So how do we discuss this time periods? How do we, because you can't just keep always saying rocks are 340 million years ago or 270 million years ago. And frankly, our way of dating rocks is precise, but it's not that precise. We can't give you an exact year or an exact day when a rock was formed. So geologists use more of the relative age, right? And they do this through this really fascinating approach to using its own sort of vocabulary. And you've probably heard about geologists refer to a rock that came from the Cenozoic era or from the Precambrian era. Well, that's what we're going to be learning about today. And these are just different ways to approach time. Here in a minute, you're going to see just sort of like a rough corollary, like an eon. You can have eons, and then you'll have eras nested with eons, and onward and onward. So The highest sort of order, you could think of this as almost like a year. Um, so if I were to say October 10th, 2020, then the 2020 might refer to the super eon. And so the super eon is really only applies to a single idea, and that is the time before the Cambrian time. So this refers to the Precambrian time period. In this era, or this eon, excuse me, I have to be sort of careful with the vocabulary here. This super eon refers to about 88% of Earth's geologic time, from around the birth of the planet 4.6 billion years ago, all the way up to 541 million years ago. You can see that on this timeline here along the right side. So we only have one super eon, and it refers to that long time period, 541 million years ago to 4.6 billion years ago. The super eon is made up of three eons. In this case, the Hadean eon, the Archean, and the Proterozoic. Of course, there's one more eon that came after the Precambrian, and that is the Phanerozoic. Very, very roughly, every eon refers to about a half billion years or more. And so we can see them here. So we have the Hadean eon refers from 4 billion years ago to 4.6 billion years ago. The Phanerozoic eon refers from the present day all the way back to half a billion years ago, roughly. Every eon is divided into an era, as you can see right here. And so every era accounts for several hundred million years. And we have lots of different eras, and you won't have to memorize this for the test, of course, because the test is going to be open book, open notes. But you're going to see here that knowing the eras gives us a little bit more of a precise understanding for when a particular rock or when a particular geologic event occurred. So if I were to say, okay, we had a geologic event that occurred around a billion years ago, well, that might be the middle era of the Proterozoic eon and the Precambrian super eon. If that doesn't make quite sense right now, don't worry, we're going to return back to this in just a second. All right, so every era is divided into periods. And so every period represents about 100 million years, roughly speaking. And so we can see some of the periods that you see here. And you've probably heard about this, especially when you were young and you were learning about dinosaurs. So the Cambrian period, or the Permian period, or the Mississippian, or the Jurassic period. And so those are account for roughly 100 million years. And so in the present period, we're in the Quaternary period. Epochs are the divisions that are inside periods, and every epoch accounts for about tens of millions of years. And so you can see all the epochs that are up here. We have the Holocene epoch, which is part of the Quaternary period, which is part of the Cenozoic era. You can see how this gets complicated pretty quickly. There's one more sort of geologic vocabulary word I want you to be aware of, and that is the age. And the age is a subdivision built into the epoch. And so the age accounts for millions of years. And you don't need to know this for the test, but just be aware that just be aware that there are more subdivisions built into geologic time. Okay, so like I said sort of right at the beginning, a fun way to think about this is to think about it sort of as nested timescales. So just as the same way you would think about the time today or the Earth today, we can sort of translate that into a geologic perspective. So we could think of, okay, if this is, and this is the correct time that I have right now, October 8th, 2020 at 11:45 and 15 seconds. So the 15 seconds would refer to the age, the 45 would refer to the epoch, the 11 would refer to the periods, the 8th of October would refer to the era, October would refer to eons, and then 2020 would refer to the super eon. This is helpful. It may be a helpful way to think about it, but something to keep in mind is that these divisions, for example, we know that there are 60 seconds in a minute. There are not 60 ages in one epoch. We know that there are 24 hours in one day. There are not 24 periods in one era. So just be aware of that, but this is helpful for me because sometimes it's weird to think about nested timescales. And so whenever you're talking about a certain geologic time, it's important to know both the eon, the era, the period, the epoch, the age that you are talking about. So what does this look like in practice? If I were to ask, explain the geologic time in 1800, you would say, okay, the eon is the Phanerozoic, which is right here, right? The era is the Cenozoic. The period, we would look over here, is the Quaternary. And the epoch that's built into the period is the Holocene. Pretty easy, right? What about the time when we first started to see reptiles, about 320 million years ago? You would say, okay, we're still in the Phanerozoic eon. Our era is the Paleozoic, which you can see right here. And then from there, we go to the period, which is going to be the Pennsylvanian, which I drew my arrow to the wrong spot, but it should be right about there. What about the time whenever organisms just began to photosynthesize? And this would be 3.2 billion years ago. You would say, okay, if you want to start at the super eon level, we would say we're in the Precambrian. And then we would go to the eon, which is going to be the Archean. And then the era is going to be the middle Archean, which is right here. What about the geologic time from this example that I showed earlier from this photo when I was hiking around in the Grand Canyon? Well, the eon would be the Phanerozoic, which is 541 million years ago to present. That's what the Phanerozoic encompasses. The Paleozoic era encompasses 541 million years ago to 252 million years ago. In that mid-white area right up here near the top, that would represent the Permian era. So we'd say that those are, we'd say those are Permian rocks right up there at the mid-level. Okay, so as you read about in your in the reading, the extra reading that you had for today, there is another epoch that geologists are talking about maybe adding. And this epoch would describe the present. It was mentioned briefly as your book that there are numerous scientists that agree that we have entered this new epoch. Numerous is a bit of a misnomer. It's really up in the air as we speak, as as that extra reading talked about. So what is this new epoch called? Well, it's called the Anthropocene. And it starts in the 1950s, maybe. Some people say it actually starts earlier, as early as the Industrial Revolution, or even going back earlier to when humans just started to move into North America. But really, what is the Anthropocene trying to show? Well, it's trying to show that humans are shaping geology. We're laying down layer upon layer of concrete and moving soils around, moving rocks around for our purposes. And so the thinking is that we are dramatically changing geology. Um, the reality, of course, is that that's not 100% true, as your reading alluded to. Yes, we are moving things around. Yes, we've changed we've changed a lot of things in the Earth's natural system, but there are some questions that are being raised whenever we begin to talk about the Anthropocene. The most, I'd say the largest question is that the epoch that we're currently living in, the Holocene, it just began 11,700 years ago. Uh, and in the way that we've treated epochs in the past, they've lasted for tens of millions of years. So that's the first concern, is why are we calling this an epoch when the current epoch, or the most recent past epoch, the Holocene, only began 11,700 years ago? Some of the questions that were raised in that reading, why name an era that you are living in? What historical event marks the start of the era? Do you start it when the first atomic weapon was dropped? Do you start it when the Industrial Revolution began? Or do you start it when humans started banding together and creating civilizations? Also, when does the Anthropocene end? Humans, as long as we can, are probably going to be making an impact on the Earth's surface. Even if it's just walking gently on the Earth's surface, we're going to have some impact. And can a single word save humanity from global changes that we brought on? So the Anthropocene is really meant to describe, according to its proponents, it's really meant to describe the major impact that we're having on the planet. So should we reduce all these many impacts, whether it's the depletion of soils, or whether it's climate change or sea level rise, or the extinction of millions of different sorts of species? Should we reduce that all to a single word and say, okay, we're living in the Anthropocene? This is something that geographers have been really engaging with too, and it's more from the discursive side. What does the word Anthropocene hide? As you can sort of read between the lines, Anthropocene, you have the first part, anthros, which refers to humans, right? So this is the epic of the humans. But what does that word hide? Well, which humans are being responsible for the Anthropocene? Is it Native Americans, or is it capitalist? Is it industrialist? Who is responsible for this world that we're living in? And so geographers have proposed other words to describe this epoch. Jason Moore refers to this as the Capilocene. Donna Haraway has occasionally referred to this as the Plantationocene, talking about the way that the plantation economy gave way to global capitalism, which then gave way to this dramatic change that we're seeing on the environment. Others say, why can't we incorporate animals into the Anthropocene? Why does it have to be a human-based epic? And so Donna Haraway wrote an entire book called The Cthulhu-cene, which describes the way that animals and humans are working together to create this crazy geology that we're living through, or geologic epic that we're living through. Other geographers say, well, maybe we should be focusing more on the chemicals that are the ones that are actually doing the work, and not the humans. And so let's refer to it as the Chemocene, as was first proposed by Nicholas Shapiro. All this is to say is that the Anthropocene is not exactly a well-defined nor well agreed upon topic. There's still a lot of discussion both within geologists, geographers, as well as in just science writ large. And so whenever you hear the word Anthropocene, just raise an eyebrow and take a critical view of it. That's what I want you to carry forward from this particular discussion, is that the Anthropocene is still something that's up in the air. So one final topic that I want to delve into before we leave geologic time behind is to focus on uniformitarianism. And that's a really big word that just says the main assumption that geologists make when talking about the past is that they assume that the processes that we see today are the processes that occurred millions of years ago. And so we can think of this in the context of chemical reactions. The types of chemical reactions that occur today in the natural environment occurred millions of years ago. Or we can talk about how water's velocity downhill or the makeup of stream water, how it might be similar today as it was millions of years ago. And so what does this do? Well, this allows us to make assumptions about what geologies were like in the past. And so that's the main thing I'd like you to keep in mind with uniformitarianism, is that it's one of those key theories of geology that allows geologists to hypothesize about the past. All right, I think now is a good time to take a quick break, look away from your computer. I'm going to grab a sip of water and I'll meet up with you in just a minute. Okay, welcome back. I hope you took a quick break. I must also apologize for the audio levels in the first part of that presentation. For some reason, the computer wasn't reading my microphone, so now I have a new microphone and it's plugged in. Hopefully it's working well. So, we are back. While the first half of the class we were talking about geologic time, now we're actually going to begin to look at the geologic processes, and I think the second part is much more fascinating, right? We're going to be looking at the center of the Earth all the way out to the crust, and basically starting at the center of the Earth. We're not going to be taking a journey to the center of the Earth like Rock Johnson did, Dwayne the Rock did, but we're going to be taking just a scientific journey, if you will. So where do we start? Well, let's start right at the center of the Earth. So right at the center, many, many miles below your feet, there's a bright inner core at the center of the Earth. And this is a solid ball with a radius of about 760 miles. And it's composed almost entirely of iron or an iron nickel alloy. And it is hot. I mean, hotter than the surface of the sun. It is really hot, 10,000 degrees Fahrenheit. So what are the main reasons for this really hot temperature? Well, the first is that there's still a lot of heat captured at the center of the Earth from when the planet and the moon were made, right? From that collision of whatever celestial body it was into planet Earth that created the moon. Second, there's a lot of heat that's generated from the friction of the iron and nickel coming to the center of the Earth and rubbing up against each other. So that generates a lot of heat that gets captured down at the center of the Earth. And then the third way that we see a lot of heat at the center of the Earth is potentially from the decay of radioactive elements. Now, why do I say potentially? Well, the reality is that we have a decent understanding of the inner core of the Earth, but frankly, it is so far away and it's so hard to measure and access using any of the instruments that we currently have that there's still a lot of uncertainty about what exactly is at the center of the Earth and what sort of occupies that inner core region. If we move from the inner core to the outer core, we find that the things change quite a bit. So the outer core, like I said, the inner core is like a really dense, thick solid. The outer core is a mostly kind of fluid layer. It's about 1,500 miles thick, so it's still very, very thick. And it's composed mostly of iron and nickel, and it's still pretty dang hot. I mean, 5,000 to 7,000 degrees Fahrenheit, that is really warm. And so what's the key thing that you need to know about the outer core and how it impacts the surface of the Earth? Well, the outer core is what generates the magnetic sphere. And we're going to be delving into the magnetic sphere a little bit later in today's lecture. All right, we've moved away from the core. Now we're interested in the mantle. So here we have the core here. the inner core, outer core, and now we're looking at the mantle. And this is one of the largest regions of the subsurface Earth. And it is separated from the core by what's referred to as the Gutenberg discontinuity. And that occurs at 1,800 miles below the surface of the Earth. The mantle is largely iron and magnesium oxide with a fair number of silicates. And the thing that you need to know is that the rocks in the lower mantle are very soft and plasticky, almost liquid. And that the top of the mantle is referred to as the moho. So we can, that moho would be right around in here. All right, finally, the Earth's crust. And the Earth's crust is largely composed of 8 elements, most of them being having some sort of bonding with silicon or oxygen. The thickness of the Earth's crust varies quite a bit, between 3 miles and 43 miles. The thickness of the Earth's crust at Chapel Hill, for example, is about 23 miles. So why do we have these differences? Well, we have the ocean crust, and its average thickness is somewhere between 3 and 6 miles. Now, you may hear occasionally that ocean crust is referred to as SEMA, and that is because there is lots of silica, the Si in SEMA, and then a lot of magnesium, the Ma there. Continental crust, on the other hand, is much, much thicker, as this figure illustrates, right? We have the oceanic crust, which is relatively thin, the continental crust, which is very thick. The continental crust is about 20 to 30 miles in average thickness, and it is sometimes referred to as Sial. And so the Si, of course, comes from silica, and the Al comes from aluminum. And so the SEMA refers to those primary, largely the compounds that you would see in the oceanic crust, and the Sial refers to the compounds that you would normally see in the continental crust, that being silica and aluminum. The temperature rises as you go down with depth. So for every mile that you descend through the Earth's crust, you're going to increase the temperature by about 75 degrees. So it can get pretty hot pretty quick. So one more way I want you to think about the deep surface is the difference between the lithosphere and the asthenosphere. So the lithosphere refers to any area that is from the surface of the Earth all the way to about 125 miles in depth. So what does this incorporate? Well, it incorporates the surface of the Earth, the lithosphere, as well as the top portion, the very, very top portion of the Earth's mantle. Now, the lithosphere is broken into pieces, which are called tectonic plates, and we're going to be returning back to tectonic plates sometime next week when we begin to talk about earthquakes, for example. But all you need to know is that the lithosphere, for right now at least, is that the lithosphere is broken up into various sorts of plates. Now, the asthenosphere is from about 60 miles, although usually it's a little bit closer to 100 miles, all the way down to 450 miles below the surface. And so as you can see here, the asthenosphere is really plastic. It's kind of molten-y. The materials move around quite a bit, and this is due to convection currents. So you learned earlier in the semester about convection currents related to the atmosphere. We have the exact same process that's occurring in the subsurface, right? Because it's warmer, closer to the center of the Earth, and cooler the further from the center that you get. And so as that molten rock rises, it cools and it starts to move, and then it descends back down into the center of the Earth. And that creates a current. And those currents is what moves tectonic plates around the surface, or more specifically, it's moving the entire lithosphere around the surface. And so, again, this is a topic that we're going to come back to in a few classes. Okay, The final key topic that we're going to be covering today is the Earth's magnetic field. So the Earth's magnetic field, not family, that's a little bit of a typo there. The Earth's magnetic field comes from the outer core, right? We were talking about how the molten iron moving around the outer core generates some magnetism, right? Earlier in the semester, you learned about true north. I think that was in like chapter 1 when you were talking about the various directions. Now we're going to take and complicate that a little bit. We're going to talk about magnetic north, which is the way that the compass needle points. And so I have a quick example. As some of you may already know, or as I may have mentioned earlier in class, I used to fly planes when I was back in high school. And the main airport that I would fly out of was Sycamore Strip, which is an airport just south of Fort Worth. And so every time we'd get into the plane, I would have to reset the compass because the compass had been floating around and had some imprecision built into it. And so I'd always have to reset it to either true north or magnetic north. And so and this is important because whenever you're lining up on the runway, you want to know which heading you're going. And so for the runway that I was flying out of, which was typically runway 17, its magnetic heading is 175 degrees, whereas its true heading is 182 degrees. So that's a pretty significant difference. That's a 7-degree difference. So if the compass wasn't aligned properly, then I might have pointed my plane in the wrong direction whenever I would take off. One of the key things you need to know about the magnetic North Pole, which is different from the true North Pole, the true North Pole will always, be to your north. The magnetic North Pole, which is critical for navigation, as I just showed, is moving. And it is always moving. So, and currently, at the present pace, it's moving at about 37 miles per year, and it's moving away from Canada and has just transitioned into the northern part of Russia near Siberia. Actually, more specifically, it's still in the Arctic Ocean, but it's sort of crossed that invisible boundary from Canada into Russia. This is important because, and this is, if I go back here, I can tell you that the FAA issues guidance to pilots every year telling them, all right, this is how much you need to correct your compasses by because the magnetic North Pole has been moving. Now, the magnetic South Pole does the exact same thing. It also moves, but it doesn't move at the same rate. The North Pole, as I said, is currently moving about 37 miles per year. The South Pole is moving at about 3 miles per year. So quite a bit less. So this is to state that the magnetic north and the magnetic south poles are not antipodal. And so when you think of an antipodal, you would say, okay, you have a marker on one side of the sphere, and then on the complete opposite side of the sphere, you're going to have another marker. This is not the case with planet Earth and the magnetic sphere, right? Magnetic North Pole is not always going to be completely antipodal to the magnetic South Pole. That's just something to keep in mind. All right, our final topic that we're going to be delving into is geomagnetic reversals. And this is something that you may have seen on, Late Night on the History Channel or Discovery Channel. What happens if the North and the South Poles flip-flop? And there's always someone who says it's going to be the most apocalyptic thing to happen in the history of humanity. Odds are it probably wouldn't be that way. And it's true that the South and North magnetic poles do swap on occasion. But the reality is that the magnetic field does not ever, quote unquote, disappear. It may weaken slightly, maybe by 20%. In which case we might get a little bit more solar radiation. We might receive some more impacts from the sun whenever that occurs, because as you learned earlier, the magnetic sphere does a fantastic job of protecting the Earth from some of the more harmful effects from the sun. So there would be a slight change in that. but it would not be the end of the world. So, why are geomagnetic reversals important for geologists? Well, it turns out that geomagnetic reversals can tell us when certain rocks were laid down. And so all the rocks would maybe pointed in one direction during one period, one time in which the North Pole was actually at the North Pole. Then when the geomagnetic reversal occurs and you have the magnetic North Pole switching to the South Pole, the rocks are going to change orientation. New rocks are, not the old ones. The new rocks are going to change orientation. And so, and with that in mind, we can actually go back and pretty well date when all the previous geomagnetic reversals have occurred. And it really does happen somewhat occasionally. It's not a big deal when it does occur. But all this is to state is that geomagnetic reversals are very useful kind of markers that geologists use to talk about when particular rocks came into existence. All right, that wraps things up for today. We have an assignment that is currently ongoing. That is going to be due on Friday evening. We also have an active forum post related to the documentary that you watched on Friday. The response to your classmate is due by Thursday evening. And then our next class is going to be on hydraulic fracturing, also referred to as fracking, as well as oil, gas, coal, and other hydrocarbons. This is my wheelhouse. This is what I study day in and day out, so I am super excited to share some of my knowledge with you, and I can't wait to answer your questions related to oil and gas and coal, especially since they've become such political, for lack of better words, materials over the last couple decades. And so if y'all have any questions, go ahead and save those up, and I'd be happy to answer them on Friday. And of course, if you have any questions or concerns about the course, be sure to reach out to me or Critty. We're here to help you. And thanks so much for listening in today. Hope you have a great rest of your week and look forward to seeing you on Friday.